Today's lesson is on systems of linear equations. First, we need to define what a system of linear equations is. It is two equations that contain two variables and have straight line graphs. Now we've graphed these things before, so x plus y equals 3 because it's got an x and a y, and there's no squared or square roots or any other interesting things there. When you find a set of solutions and graph them on a coordinate plane, this will turn out to be a line. Now these two equations are together, they're right on top of each other. That means that they're together for some reason. There's some reason why someone put those restraints together, and those two equations together make a system. The next system we have is y equals 2x plus 1, y equals 3x plus 2. Notice those are in slope-intercept form, but they're a system because someone put them together. And the next one is another example of two equations that contain two variables, and they together make a system of equations. Now there are several methods that we're going to learn to find solutions to these types of linear equations. In this particular section, we're going to be talking about graphing. So there's a couple different ways lines can interact on a coordinate plane. Lines can intersect at a single point, like the blue line and the red line intersecting right there. You could have two lines that are parallel and never cross, like the middle graph. And then you could have two lines that coincide. This one's kind of hard to see. So the red line you can see, but the blue line you can't see because it's underneath. So there's like a red line and a blue line right on top of each other, so that you can't actually see both of them at the same time. That means they're the same line. They may have different equations, but they're going to be the same line in the end. So if you have the first example where you have the blue and the red line intersecting at one single point, how many solutions do you have? Well, you only have one solution. This type of system is called an independent system. It's independent because the blue line has nothing to do with what the red line is doing. They're totally doing their own thing, and they happen to cross at some point, but one doesn't tell the other one what to do. They're totally independent. The solution example would be the intersection point, x comma y. Or, like in this case, this point looks like, and I'm just guessing here, about 2 comma 1. So over 2 and up 1 might not exactly be correct, but I'm just kind of estimating there. On our next example, we have two lines that are parallel and never cross. How many solutions do they have? Well, the blue line is never, ever, ever going to touch the red line because they have the same slope and they're going in the same direction and they're never going to cross. So how many solutions? None. The type of system is called inconsistent. The two lines don't interact with each other at all, so we don't have any data on this at all, which is why we call it inconsistent. What is the solution? Well, the solution is called no solution. You can either write NO solution here, or you can do the circle with a line through it, which means no solution. The circle with a line through it does not mean 0, okay? In our last example, or when the two lines coincide, how many solutions are there? Well, there's a lot of solutions. Every point on this line of the red line is also on the blue line. Every single point. So how many solutions? Well, there's infinitely many solutions. The type of system, we call it dependent. Remember the first line where they intersected was called independent because the blue and the red did their own thing and they didn't rely on each other. Well, this one's called dependent where the lines coincide because whatever one equation is, that's what the other one is definitely going to be. Now the solution example is really much different than anything you've seen before, and I know you've seen an ordered pair before, I know you've seen no solution before. We have to write every single point on that line. Well, we would be here all day long if we sat here and did that. So we're going to use this set notation. So it's a little brace, okay? So little squigglies. We're going to say this is called the set of all points x, y, such that there's a straight line. It's called such that. And then what you're going to do is write one of the equations of the line. For example, 2x plus 3y equals 6. I don't even know if that's the equation of this line, but nonetheless, that's what we'll give you an example there. So this set notation is read, the set of all x, y such that 2x plus 3y equals 6. The set of all x, y such that equation. That's equation right there. I didn't have enough space. Okay? All right, so let's look at some examples. Find the solutions of the following systems using the graphing method. So on our first problem, we have two lines that intersect. Now, this has already been graphed for us. Hooray. So we don't have to do that. All I have to do is look at the intersection point, and the solution is 2, 1. On our next problem, we have two lines that are parallel, and this line over here is never going to touch that line over there. They're never, ever going to reach. So the solution is no solution. You could also write the symbol for no solution, either way. And our last example are two lines that are the same. Do you see that x minus y equals 3 is written right here? And then 2x minus 2y equals 6 is written right here, but it turns out that they're both the same line. So what is my solution? Okay, this one's the tricky one. It's the set of all x, y, so little braces, and then an ordered pair x, y, such that, so that's that vertical line. And then you just write one of the two equations. I don't really care which one you write, because they're essentially the same, because the two equations, even though they look different, give you the same line. So that is the solution. A lot of students at this point want to just say, oh, there's infinitely many solutions, and move on. If you say infinitely many solutions, all you're doing is telling me how many solutions there are. You're not actually telling me what the solutions are. So now we're going to actually have to graph our own problems and then figure out what our solutions are. So on this problem here, I'll do the first one in blue and then the second one in red, I think. Just making these colors so you can tell which I'm doing. So I found that most students prefer to graph in slope-intercept form, and these aren't in slope-intercept form. So the first thing I'm going to do is write the blue equation and solve it for y. So I want y all by itself, so that means I minus x from both sides. Now this gets some students confused because they have 8 minus x. I really prefer the x in front and then the plus 8. Now a faster way of doing this is just picking up the thing that you don't want on that side and moving it to the other side, and anytime you pick something up, a term up and move it to the other side, it just changes sign. So I'm going to start showing you how to do that instead of the minus, because it just takes up more space, and it's going to be a little bit helpful to you. So my m for the blue and my b, now that I've got the y all by itself, the m is the number in front of the x, which in this case happens to be -1, or I can think of it as a fraction of -1 over 1. My b is 8. So I'm going to come up here to 8 and put a dot on my intercept, and then I'm going to go down 1, right 1, down 1, right 1, because that's what my rise over my run tells me to do. -1 is down 1, +1 is to the right. Now I'm going to do this all the way off. Now I find in systems of equations it's helpful just to leave those dots as is until we do the next one. You could draw a line, but sometimes when you draw a big fat line it's hard to see where the two things intersect, especially when they have similar slopes. So I'm just going to go ahead and leave that blue one as dots for the moment. I'm going to rewrite my red equation. I want the y to be all by itself, so who needs to move? Well, it's the x. Remember how I told you we're going to use transposition? If I pick the x up and move it to the other side, what happens is its sign, which was negative, changes to positive. So I have y equals x plus 2. The m is simply the number in front of the x, which is 1, or I can rewrite that as 1 over 1. My b is 2. So I put my first point at 2 on the y-intercept, and then I'm going to rise 1 and run 1. Rise 1, run 1. Rise 1, run 1. If I continue to do this off my paper without having the extra lines in there, just the dots, the spot where the two dots are on top of each other, that is going to be my solution. So the solution to this problem is the ordered pair 1, 2, over 3 and up 5. So 3, 5 is my solution. Okay. Now if you want, at this point, you can go back and draw your lines. I just find it helpful to not have it drawn right in the beginning. That one was probably going to be easy enough that you could see it, but nonetheless, I just was a little bit careful. So here I have the next problem, I have a blue equation, I'm going to have a red equation. I'm just trying to keep them consistent so you can see. Neither of these are in slope-intercept form. So if I pick the 3x up, because I want the y to be all by itself, right? If I just pick that term up and move it to the other side, the positive 3x turns into negative 3x plus 6. So I just picked it up and put it over. I like the x in front, so I go ahead and put it there. Then I have to divide everything by negative 2 so that the y is all by itself. So I have y equals negative 3 over negative 2. The negatives divide out, and I just get positive 3 halves. Positive 6 divided by negative 2 is negative 3. This gives me, my m is 3 halves, and then a lot of people are like, oh no, fractions. We actually like fractions in the slope, right? So that's rise in the top over run. So don't worry about the fractions in the slope. I'm going to put my first point at negative 3. Then I'm going to rise 3, run 2. Rise 3, run 2. Rise 3, run 2. All the way off my picture. Now I could also go down 2, left 3. That's also on my picture. Again, I would recommend not actually drawing your picture here. And let's do the next problem. We have x minus y equals 1. Move the x over, that gets me negative y equals, the x changes teams, right? He's going from the team on the left to the team on the right, so that means he's got to change a sign, which is negative. And then I'm going to divide everything by negative 1. This gets me y equals positive 1x minus 1. So the m is 1, or really 1 over 1. My b is negative 1. I put my pencil on the b, which is negative 1. Rise 1, run 1. Rise 1, run 1. Do you see how if I drew the lines, you might think that they cross there, but they don't, because the points have to cross. Rise 1, run 1. That doesn't cross yet either. Rise 1, run 1. Now it crosses. Okay, do you see the one point where they intersect? The one point where they intersect for this particular problem is going to be my solution, which is, let's see here, 4, 3. And I can see that with the dots. Now, when we come back and put our lines in, no matter how straight I can draw my lines, you can see that it could be very unclear where it actually crosses. Some students might think it crosses here, some things might be above it, but because we just used the dots only, it was very clear to see where the actual solution was.